Okay, so I want to continue talking about this model from last week, and that is called, the best way to call it is inequity aversion. The model of inequity aversion by Ernst Fair, and Klaus Schmidt, two German economists who wrote this paper in the late 90s. I actually think it was written maybe in 96, 97, but it wasn't published until 1999. And of course, they didn't call it inequity aversion. They called it a theory of competition, cooperation, and one other thing. I forget. They didn't use the words inequity aversion to refer to their model, but of course that's what it is, and that's how it has come to be known. Let me share with you my slides on this topic. Somebody's playing keyboard in my house, and I hope they're not too loud that you can hear it. Okay. Current slide. Okay, here are some slides that we did talk about last class, but I'm going to just go over them as a little bit of a review, because what we had last class, I gave you breakout rooms. I assigned you to breakout rooms, and I gave you this question, and I asked you to get it. I think half the groups got it, the other half didn't, which meant it was probably kind of a tough question. And I would like you to be able to answer not just that question, but questions similar to that I may ask on a quiz or an exam, right? I asked you a question about the ultimatum game, but I could ask you different questions. I could ask you something about the trust game, the gift exchange game, the prisoner's dilemma game, a public good game, of course, the dictator game. Those are the main games that we've talked about in this class. But the question is, what is what we're learning now, which is the Fair-Schmidt inequity aversion model? How does that apply to these other games that we've already learned about? And I want us all to see whether or not it has some explanatory power. Okay, so let's go on. Right now, let's review a little bit of inequity aversion. With this, example. Let's do the ultimatum game first. In the ultimatum game, the most common behavior responder is to reject anything below 30%. Sometimes it's listed as 20%, sometimes it's 30%. I think in the original game, if it was between 20 and 30, it was like half and half. So let's just say for now that it's anything below 30% of the pie is rejected. That's S, the share, 30.3. And anything above 30% is accepted. What does that imply about alpha? That's a question. And maybe let's on this whiteboard, I think you're comparing what it's like to accept this offer. You're going to accept anything. Now it's 30%. Anything above 30%, you're going to accept. Anything, oops. Oh geez, I lost my whiteboard controller. Here it is. I just want this to move out of my way now. Anything below 30%, I'm going to reject. Let's take this as like an empirical result. I'm sorry for writing so poorly, but in the ultimatum game, if you are the second mover, the responder, you don't have any choice over the share that is given to you. You don't choose the fraction of the pie that you get. Only choice you have is to accept or reject. And right now we're considering what happens if I accept anything above 30%, but I reject anything below 30%. right at 30%, I'm indifferent. Would you guys agree with that? If it's equal to 30%, you sort of indifferent. The word indifferent, oops, that's a really bad typing, but the word indifferent is a fancy way of saying, I don't care which of the two outcomes I get. They're equally good to me. And in fact, they give me the same utility. And that's the point. If we're talking about a responder in an ultimatum game who thinks accepting an offer of 30% is just as good as rejecting an offer to 30%, that's the point where I change my mind. Then that means those two utilities are the same. The reason I'm going through this exercise, oh, do you have a question? No? No question? I think you're just unmuted, but okay. The reason I'm going through this exercise is to explain where that formula comes from in the Fair and Schmidt's paper. Fair and Schmidt give you this formula that says what a responder would do in the ultimatum game, but I don't think it's particularly clear to see where that comes from. And in this example, I want to talk about exactly where it comes from to try to make sense. And let's just think about what would be my utility if I accept this offer of 30%. What would be my utility if I reject this offer? And then noticing, okay, they have to be the same in this case because of the indifference. Their sort of indifference brings these two together. If I accept the offer of 30%, if it's a $10 dictator game, that's the same as saying my utility equals 3. The reason I get a utility of 3 is because I'm keeping $3, and my own payoff is always the first thing that enters in my utility function is your own payoff, 3. But I have to subtract off the feelings of guilt. I'm sorry, not guilt, envy. The feeling of envy that I feel because somebody else is getting more than you. Remember, if somebody gives you 30%, that means they're keeping 70% for themselves. And if it's a $10 gain, that means they're keeping $7. You're only getting 3. They get 7, you get 3. The difference there is 4, but I'll write that out. It's alpha times 7 minus 3. Okay? That's for accepting. What happens if I reject? Well, if I reject, my utility is, once again, it's my own payoff, which is 0. If I reject, I don't get anything. Do I need to subtract anything off? No, I don't. I'll just put in here alpha 0 minus 0, just to show you that indeed, show you that if I reject, I get nothing, but I also don't feel any envy because the other person isn't getting more than me. We're both getting 0. So in fact, this whole thing will just equal 0. You guys have any questions about that? I'm now talking about what happens in an ultimatum game where a person is indifferent between accepting or rejecting 30%, an offer of 30%. And I'm using the Fair, Schmidt, and equity aversion model to think about what the numbers are, the utility numbers are, in order to say something about alpha. That's what I'm doing. And hopefully you're following along. Actually, if you're not following along, could you do me a favor and ask a question? So like, I don't understand where that comes from. Because if you're confused, there's probably somebody else who's confused too and is just unwilling to ask. But if you stop me now and say, wait, I don't get where that comes from. What are you doing with that? Then maybe I can help not just you, but anybody else who's thinking that and too afraid to ask. You're going to use chat, huh? Not really getting it. Okay, thanks, Daniel. Let's be more specific here, what you're not getting. Do you get where these numbers come from? Do you not get where these numbers come from? Is that it? The ones I just put in the box? Yeah, okay, so let me explain where those numbers come from. They come from the fair, I'm gonna share a different file now. And honestly though, thank you, Daniel, because somebody has to say something. I want to share. Oh, maybe I have to stop sharing. No, new share slides. Okay, let's go back to the model. Let's go back to the description of the model that we're using. Remember, it's called inequity aversion. I'll go here. Okay. How come it's this? A slideshow. Do I need a slideshow? Okay. This looks rather complicated, but I kind of went through it before. I spent a long time going through it because I realized it looks complicated, and it's actually more simple than more simple than you realize. And let me go through it again because I think this is an issue that it's hard to teach to you guys over Zoom when I can't see your faces. I don't know what you're confused by, what is easy, and you're like, oh, I'm bored, I want to go on to the next thing. But my guess is this is something that you are confused by. So let me go through it again. When I say you, I mean you plural. There are two equations here. There's equation 1 from the book, from the paper, and there's equation 2 from the paper. I'm actually going to use equation 2. Do you know why? Because equation 2 is the case when there's only 2 players. If there's more than 2 players, like a 3-player, 4-player, 5-player game, then you have to use equation 1. Because you have to think about how my payoff compares to every other person's payoff. And it's more complicated. If you're lucky and the game is only 2 players, and I will say this, in an exam, in a quiz, I almost guarantee I'm going to give you a 2-player game. I'm not going to give you a 5-player game or a 10-player game. It's not worth it for me to ask you the more complicated question. I'm going to ask you the simpler type to really tell if you understand it. Okay, so hopefully that's good news. I'm going to give you a 2-player game. Because it's a 2-player game, we can just look at this equation 2. So I want to look at this equation 2 and hopefully go over it again and make it so that you're not confused as to where those numbers are coming from. What is equation 2? It says utility of player I. Who's player I? Well, it's one of the 2 players of the game. And just think that I could be anything. I could be 1 or 2, or it depends on the game. So in the ultimatum game, who are the players of the ultimatum game? Hopefully you remember this. The players of the ultimatum game are the proposer and the responder. Sometimes I call the proposer the first player, and I call responder the second player. But officially, their names are proposer and responder. And so I refers to either the proposer or the responder. Let's look at the responder, because in bringing up this example, I was focusing on the responder's actions. I said the responder has this behavior of if it's 30% or more, I'll accept. If it's 30% or less, I'll reject. Do you have a question, or are you just unmuted?
Ew, he ate my booger.
Just unmuted.
Oh, thank God. Get rid of that. No, don't go find it.
Don't find you? Why not?
He liked my booger, Michael.
Wait, do you have a question? Or are you just talking? I think they were just talking. I think I found the person, I unmuted them. Okay, where was I? In this example, the example that I started the class with, I'm thinking, how can we explain the responder's behavior in an ultimatum game? So what utility function am I going to use here? Ui of x. I'm going to think that I represents the responder now. So I'm thinking of what is the responder's utility? I'm going to use equation 2. Hopefully you can see equation 2. Ui of x means the utility of I, which is the responder of the outcome, or the outcome x. What is it equal to? I'm going to explain each term. Ui of x. Hopefully that made sense. Utility of the responder given the outcome x. X just represents the outcome. What is it equal to? The very first term is xi. What is xi? It's the payoff of player I. So if you're the responder, if I is the responder, xi means the payoff of the responder. That's where the 3 comes from. Remember in that black box, I put a rectangle about it and I said, Daniel, is this, you don't understand where this is coming from? He said, yeah, I don't get that. Here's where it's coming from. This xi says it's the payoff of the responder given this outcome where somebody offers you 3 out of $10 and you accept it. Somebody offers you $3 and you accept it, then your payoff is 3. That's why xi is equal to 3. Okay? The minus sign is a minus. Alpha I left as an alpha. I left that as an alpha because we don't know what alpha is yet. Okay, so x was 3, so it's 3 minus alpha. How about this term? This term says the maximum of xj minus xi comma 0. That means if the other player is getting more points than me, more payoff than me, then I write down xj minus xi, where xj is the other player and xi is me. So in this case, it would be in the ultimatum game where you accept a 30% share, I have to write this down. I have to write down 7, xj, the other player, is getting 7, minus xi, 3. So that's why I wrote 3 minus alpha times 7 minus 3. This term exists because 7 minus 3 is positive, and the maximum of a positive number in 0 is the positive number. So that's where 3 minus alpha times 7 minus 3 comes from. What about this part, this beta part? Well, this part comes from the guilt if you're getting more than someone. xi minus xj, that's my payoff minus yours. If this is positive, that means I'm getting more than you and I would feel guilt. But in this example, that doesn't happen, right? Because I'm getting the smaller share. So I therefore feel no guilt. I didn't write this part at all. I just skipped that part. Okay? So I'm using this formula and I'm realizing the alpha part will exist, but the beta part won't. The beta part I can just ignore. And let me say this too, this is a hint, this is a strategy for thinking about this in the future. There will always be either one or the other, but not both. You can't have, in the 2-player game at least, either you have a higher payoff or you have a smaller payoff, but you can't both. You can't have the alpha and the beta. And I hope this isn't confusing. So, if you understood that, let me make another point. In the multiple player case, then you could have alpha, you could feel envy with respect to certain players and guilt with respect to other players because there are multiple other players. That's equation 1. But for equation 2, there's only one other player. And either you will feel envy, this alpha term will be positive here, or you'll feel guilt, and this beta term will be positive. Or neither. If it's equal, then these both go away to 0. So Daniel, will you be my sort of guinea pig right now? Do you understand now where that I'm using this formula to come up with what was in the box? Does that make sense? That's not really a yes. Let's look back at the box. I'm gonna go back and look at the box and follow with me if you will, the whiteboard. Remember what was in this box? Utility equals 3 minus alpha 7 minus 3. The 3 is the xi. The minus is the minus. The minus doesn't change. This alpha, it was written as alpha I. The reason I dropped the I is because there's only one player here that we're really talking about, and that's the second player. So I dropped the I, but it's there. What was the set? Then it says times. I'm writing down what the formula said. It said max. Oh, sorry, I'm so bad at using this. xj minus xi. I'm getting better. Comma 0 and braces. Okay, this is what it said. Remember? I don't know what that is. Oh, dang. trying to make this look nicer. Okay, this is I think this part said U I X equals, okay. So now I've written down exactly what was from the formula on my slides. And that formula from my slides, I got exactly from the paper, from the Fahrenschmidt paper. I literally like screenshotted it, or I don't know, somehow like copied it from the paper and put it in my slides. And it says this, what's written down here. Let me use a red. You know. Oops. This red box is equation 2 from the paper. Okay? Oh, mine, I didn't include the beta part because we can ignore the beta part. Daniel, you with me? Sorry, I'm picking on you. You're nice to me because you answer my questions when I ask them. Okay, so this red box came from the paper. I want to apply that now. I want to use that for a real world example, which is, let's think about the responder in an ultimatum game who accepts an offer of 30% of $10. Okay? We want to use what we have in that red box to say something about a responder in an ultimatum game who accepts an offer of 30% of $10. Let's do it. It's going to be what's in the blue box. How do I know that? It's because just think about what each of these terms are. Use the numbers that you have, because here's what I should say. Xi equals 3. Xj equals 7. Because in an ultimatum game, your payoff, if you accept 3 and the other guy gets 7, you get 3 and they get 7. That's what Xj means. Xj is the other guy's payoff, it's 7. Xi is your payoff, which is 3. If you're confused by this whole maximum thing, you can just ignore the maximum and say, well, only do it if you actually have some envy. If you actually have some envy, then ignore the maximum and just include this term. Do you see how you get from the red box to the blue box? I'm just plugging in the fact that Xi equals 3 and Xj equals 7. Okay? I mean, if you want, you can think about the fact that the maximum of 7 minus 3 and 0 is 7 minus 3. Okay, okay. So that's what I did when thinking about a person who accepted the offer. Good, 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 good. Now I want to think about the person who rejects an offer. Well, it's the same formula. Okay, let's use green. This red formula, it's the same formula that I'm going to use, except the difference now is Xi equals 0. So maybe I should do this. I have an idea. Here in the green, Xi equals 0 and Xj equals 0. Okay? Oh, I think this is clear. I think this is a clever teaching tool to use colors like this. Not that I'm saying you can't learn it without the colors, but the colors just maybe make it more clear. Here, Xi equals 3. That's supposed to be a 3. And Xj equals 7. But that's the only difference. The only difference. Okay, so in the blue box, we plug in Xi equals 3, we plug in Xj equals 7, and we get that. In the green box, we plug in Xi equals 0, Xj equals 0, and we get this. We basically get two numbers. I'll keep this situation where I use blue here. This actually is equal to, what is this equal to? 3 minus 4 alpha, isn't it? 3 minus 4 alpha. That's just some algebraic simplification. And here in green, we have 0. That should have been a 0. Now, so all I've done so far is to say, well, if you accept, you get a utility of 3 minus 4 alpha. If you reject, you get a utility of 0. Both formulas came from the red box, but just different things were plugged in. I'm still not done. Now I want to say, if I'm indifferent, then those two utilities should be the same. And that means 3 minus 4 alpha equals 0, doesn't it? That's where this indifference comes from. I should circle it with both the green and the blue. They should be the same. So if 3 minus 4 alpha equals 0, I can solve for alpha. What do I get? If I know that 3 minus 4 alpha equals 0, if you add 4 alpha to both sides and divide by 4, you get alpha equals 3/4. Okay? This is using the model to solve for alpha in this particular game. I would like for you guys to be able to do this. And, you know, it sucks I can't be there in person to do this on a whiteboard, and like I think I could explain it easily in person. It's a little tougher over Zoom. But hopefully you get this idea that we're using the model to infer. The word is infer. You're inferring the value of alpha for this player. Somebody plays the game, you observe what they do, and from that you infer their value of alpha. And this is a common behavior in the ultimatum game. And therefore this is our conclusion. Our conclusion is, you know, a typical value for alpha for people who play this game is about 3/4. And that's right. Okay, I think I should go on. I think I should go on. Yes, Amina, good question. If you reject, the other player gets nothing. That's the whole point of the ultimatum game. Sorry, I still haven't figured out how to not be so bright. I gotta get some blinds. Okay, Amina, if you reject, the other player gets nothing. That's why those green xi equals 0, xj equals 0 also. So let's look back at my slides, and I think it'll make more sense. Here, here, there. Here we go. Current slide. Okay. Nope, this wasn't the current slide. Here. So I've asked this question here. The second bullet point is the question that I've spent the last 20 minutes talking about. I've spent a lot of time just answering this question here in this bullet point. What does that imply about alpha? And the answer is in this bullet point of the first sub bullet of the last bullet. From the ultimatum game, we know the responder is indifferent between accept and reject when offered 3. So if you equate the two utilities, you get 3 minus 4 alpha equals 0.75. That was all the math that I just did. Was just to get to this conclusion here, that alpha equals 0.75. Okay? And I'm happy to do it because my job is to try to explain this to you. And I don't want it to be confusing. I want to help. Okay, so that's the answer to this second bullet point. What about the answer to this third bullet point? I don't think we've done this one yet. Haven't done this one yet. The dictator game, the most wait, have we? Have we done the dictator game yet? I don't think so.
We haven't done it with this equation.
Okay, thank you. So read what I wrote here. What does giving nothing imply about beta? If you see a dictator who gives nothing out of $10, he keeps it all for himself. What does that imply about beta? Do you guys have any answers just like off the top of your head? Without
beta equals 0?
That beta would be 0? Good,
Yeah.
good guess. Because what you said, the reverse is correct. In other words, what is it? Inverse, converse. If somebody has a beta of 0, then they will give nothing, right? That is correct. But if they give nothing, does that mean their beta has to be 0? Actually, no. And here's why. What if, just as a reminder, beta is guilt. Beta is how much guilt you experience. If you experience a little bit of guilt about keeping the money for yourself, Does that mean you're going to share the money? No, it doesn't. Just because you feel a little bit of guilt, that's not as strong as the pleasure you get from having the money. You guys get that?
I thought the equation, could you show it mathematically?
Yes, I can show it mathematically. But before I do that, I want to just think about it. All this math is worthless if it doesn't make sense, right? What's the point of doing all these equations if we don't actually believe what the thing is saying? And I wanted, before I do the math, I'm sorry, it's going to be more boring math. If you hate math, this is not going to be a fun day for you, but it's actually not that much math. And I can explain it. I can get the intuition to explain everything I do mathematically if you want it. Here's my point. And Peter, I'm glad you're pushing back on this, because it's always fun to push against something. And so you're saying, if I feel guilt, then I should share some of my money.
Exactly.
And I'm saying the reason that's not true is that if I keep all of the money for myself, I get that big payoff of 10. If I share any of that money with you, I'm going to have less money for myself. However, I will feel less guilt because I'm not screwing you over as bad. If I share something with you, then my guilt will go down. But how far will my guilt go down? It depends on the parameter beta. So if beta is really small, then the amount of the amount of guilt that I feel, the reduction in guilt is also very small.
Okay, so like your original utility would drop more than you would gain from getting rid of some of that guilt.
Yes, yes. If you have a small beta, let's say your beta is 0.01. 0.01 is your beta. If you play the dictator game, you're going to keep all the money for yourself. Will you feel bad about it? Yes, a little bad. You'll feel a little bit bad because 0.01 is not 0, it's 0.01. But you will just say, well, whatever. Yeah, I feel a little guilty about it, but I'm going to keep the $10. So beta, it matters how big beta is. It does.
So
That's what I'm saying.
Would the like break-even point be at beta equals 0.5?
Yeah.
Okay.
You did the math. Did you do the math or were you guessing?
Well, that just kind of makes sense because like for each amount that you lose in utility, you need to be gaining an equal amount in the opposite of guilt.
That's perfect. Sorry if I'm playing favorites with my students. I should treat all of my students the same. But Peter's answer of, so this question here that I asked, the second bullet point from the dictator game, it's not so simple. What does it apply about beta? Any ideas? He basically gave the right answer and he gave the right intuition, which is that there's a cutoff point of beta equals 0.5. Right at that cutoff point of beta equals 0.5, it becomes worth it to give money in the dictator game. Why? Because every dollar you give reduces your guilt by, reduces the difference by $2. It's doubled. Does everyone see why that's true? If I'm playing a dictator game, I could keep $10 for myself, or I could give you 1 and giving myself 9, leaving me with 9. So by losing $1, going from 10 to 9, I've decreased our gap by 2, because the difference between 9 and 1 is only 8. The gap went from 10 to 8, but I only had to pay $1. So that's where the beta equals 0.5, this idea of 1/2. Why is it 1/2 and not just 1? It's 1/2 is the cutoff point because sorry if my head is lit, I haven't even been looking here. Because there's a ratio of 2 to 1 of how much of the gap I can pay $1 to reduce our gap by 2. And the question is it worth it for me to do that? And it depends on your parameter beta, because the benefit I get from reducing our gap is equal to beta times the reduction. So if it's a $2 reduction, I multiply that $2 times beta, and I compare that to the $1 that I'm losing for myself. So 1 equals 2 beta is the equation. If you solve for beta, you get beta equals 1/2. I think I have it written on the slide. So intuitively, that's where this comes from. The answer to this question I have posed. Like, what does it imply about beta? If you think about the dictator game, what does it imply? Well, if you see somebody who gives nothing, it means their beta is somewhere between 0 and 0.5. Okay? Because they may feel some guilt. They may feel bad about keeping all of their money, but they're still going to do it because the amount of guilt they feel is less than the preference they have for keeping the money. At 0.5, they become indifferent. They become indifferent between giving money and keeping it. And if beta is greater than 0.5, then what will happen? What will happen if a dictator has a beta greater than 0.5?
Then they'll definitely want to give up something.
How much?
That's what the math tells you. I don't know.
It does, yes. So we can look at the math, or we could try to intuitively think about it. Every single dollar I give lowers the gap by 2. So if my beta is greater than 0.5, let's say my beta is 0.8, which is greater than 0.5. I just picked 0.8. Every time I give $1, I'm reducing the gap by 2. And if I take that 2 times 0.8, it's like 1.6. I'm like improving my utility by 1.6 every dollar that I give. I'm losing $1 of utility, but I'm gaining 1.6 in inequity aversion. When will I stop giving the dollars? I'll give the first dollar to make it 9.1. I'll give the second dollar to give 8.2. I'll give the third to make it 7.3. I'll give the fourth 6.4. I'll give the fifth. It'll be 5.5. Will I give you another dollar? No. I won't give you more than half, because by then I no longer feel any guilt. I'm not helping anybody by giving you more than half. I'm not helping myself feel less guilt. So the answer is the Fair-Schmidt inequity aversion model makes a stark, the word here is stark, prediction in the dictator game, which is if beta is less than 1/2, you will give nothing. If beta is greater than 1/2, you will split the money in 2. You will give the recipient half of your money. And you may say to that, wait a second, we see people don't just give half or nothing, they give something in between. In fact, the average is something like 16, what is it, between 10 and 20% is what's given in the dictator game. And a lot of people give something between 0 and 5. How do you explain those people? Does that mean the Fair-Schmidt model is broken and can't explain anybody who gives $2? I wrote that here if you look at the slides. What about $2? What if somebody gives $2 in the Fair-Schmidt inequity aversion model? Well, it can actually still be explained if your beta is exactly 0.5. Because if your beta is exactly 0.5, you are sort of indifferent between any amount of money that you give. You might give $2 and keep 8 for yourself because simply you're indifferent between doing that or doing something else. I should say, I personally have used other models that don't have this linear assumption. The reason you get this funny behavior at beta equals 0.5 is because this is a linear model. And when you try to solve a linear model using optimization, you get these sort of corner solutions often. And the dictator game is an example of a game where there's a corner solution, C-O-R-N-E-R, corner solution, because either you'll give nothing or you'll give half. It's like one or the other. It's a very stark prediction. And the reason for that corner solution, not coroner, I didn't say oh. You knew that. Got it, corner. Yeah. So yeah, some levity is in the situation is probably useful. Okay, so let's look at the slides because I will say what I just said only in the slides. Yeah, how come I can't? There we go. This is exactly what I said in words, but now here in slides. What is the dictator's cost for giving $1? The answer is 1, because they lose $1 in their utility. Remember the formula. The first thing that goes into it is your own payoff. So if you give $1, you lose that $1 of your own payoff. That was this question. How about in terms of utility, what's the dictator's benefit for giving $1? Well, by giving $1, you reduce the inequity by $2. I explained that. This reduces the disutility received from experiencing guilt by 2 times beta. So the benefit is 2 beta. You give $1, you lose a utility of 1, but you gain a utility of 2 beta. Question, if we see the dictator giving nothing, what does that mean about beta? It must be that the cost of giving was higher than the benefit, or 1 minus 2 beta, so beta equals less than 1/2. That was the conclusion that we had, remember? If you see the person giving nothing, it means their beta has to be somewhere between 0 and 0.5. I know this because beta cannot be negative, so it has to be between 0 and 0.5. Question, if we see the dictator giving 5 out of 10, what does that mean about beta? Well, that means the benefit of giving was higher than the cost, so 2 beta was greater than 1, and the dictator gave until there was no more benefit because the payoffs were equal. So beta would be greater than 1/2. So this is a little less satisfying than the ultimatum game where we could get exactly the value of alpha. In the ultimate, remember, let's go back here. We got exactly the value of alpha was 0.75. In the dictator game, we didn't get to nail down what beta is. We only get these regions. The regions are if they give nothing between 0 and 0.5. If they give half, then it's something greater than 0.5. If they give $2 or anything in between, if they give some money but not half of the money, then actually the prediction is beta equals 0.5. Okay, I think I have that. I have that on this slide. We have a corner solution of giving $5 or giving $0. This is what I said before. This is just the slides which go over what I've already said. If we see someone giving between 0 and 5, this can happen only if beta equals 0.5 or utility doesn't depend on X. Don't throw out the model. So alpha greater than or equal to beta seems to be confirmed. At least in this case, doesn't it? Because when you look at the most common outcome in the ultimatum game, it gives you an alpha of about 0.75. And when you look at the most common outcome in a dictator game, or at least a very common outcome is for people to give some but not all of their money. It's a very common outcome. That means beta has to be around 0.5. And that's a good ballpark that says alpha 0.75 is greater than beta, which is 0.5. Of course, this is imprecise. And there's a lot of heterogeneity. Heterogeneity is a fancy word for there are a lot of differences. There are a lot of different types of players, of people. And these are averages, right? When we talk about the average alpha being 0.75 and the average beta being 0.5, it doesn't mean that everyone's alpha is 0.75 and everyone's beta is 0.5 because of the heterogeneity. Okay, I think I have to go on so we don't spend too much time on this. Here's a major conclusion of the Fair and Schmidt paper. The principle of equity aversion can explain self-interested outcomes in some environments, like the fact that there's seems to be exploitation in markets, or the fact that there's declining cooperation in public good games. But it can also explain the pro-social outcomes in other environments where, like the ultimatum game, people seem to care about fairness in these just one-on-one bargaining situations. And people seem to cooperate pretty well, often, not all the time, but often they cooperate in Prisoner's Dilemma games too. Certainly in Golden Balls, about half the time, people are choosing to share the money instead of doing the self-interested thing, which is try to steal the money. Okay. Talk a little bit more about this. In large markets, a single player cannot enforce a fair outcome. Okay, that's just true. If you're just a buyer in a market, you can't control what other people are buying and selling the product for. All you can do is on your own say, yes, I will buy that, or no, I won't. And there's going to be some inequity, whether you want there to be or not. And therefore, it sort of washes out the inequity aversion part, just sort of becomes irrelevant because of that dividing by n and because you have no control. And it looks pretty much the same as the standard model. I don't know if I'm sorry, I'm going to go way back to the formulas again. Remember this formula? Oops, where is it? No. There. These formulas, if they just stopped at xi, that would be the standard model. Okay? If equation 1 and equation 2, if the only thing that was included was xi, that would exactly be the prediction, the assumption of standard economics, which is that you care about your own payoff and you seek to maximize your own payoff. So you can think of this model as if everything to the right of xi were just to disappear, it would be exactly the standard model of economics. And the good thing about Fahrenschmidt is that in those cases where we can ignore everything to the right of xi, in those cases where we can ignore all of this stuff, people are going to behave exactly like they do in the standard model, like in a market, a big market. And that's kind of the good thing about this paper. It can say, yes, sometimes people are selfish and self-interested, other times they're not. Do we have time to do this Monopoly game thing? My clock. Yeah, let's think about it. I think I have time. It's 1:21. Okay, let's get going. Let's say a monopolist. Okay, I'm explaining a new game to you now. Okay, it's like the ultimatum game, but it's a little different. So hear me out. In this game, there are 4 players. One of the players is called the monopolist. What does the monopolist do? He or she offers a price, P, and if somebody buys the product that they're selling, someone accepts this offer, then the monopolist gets a payoff of P if somebody buys their item. They get a payoff of 0 if no one buys their item. Okay? How about the buyer's payoff? The buyers get a payoff of 10 minus P if they buy, 0 otherwise. You understand this game? I've explained it with just 2 very short sentences. Let me try to make sense of it to you in another way. This is exactly the same as the ultimatum game if there's only one buyer. If you think of this game as with there only being one buyer, this is exactly the ultimatum game.
One seller, you mean, right?
No.
What?
So,
Isn't the monopolist a seller?
The monopolist is a seller. So in the Monopoly game, there's one seller and many buyers. Okay? What I'm saying right now is that if there was one seller and one buyer, it would exactly be the ultimatum game. Because then the monopolist is like the proposer, offering a price, which is really like offering a share. And then the buyer becomes like a responder because they either accept the price or reject the price. That's the same as accepting or rejecting the share of $10 that they get to keep.
Yeah.
Make sense?
Yeah.
Okay. So you can think of the Monopoly game as an extension of the ultimatum game, where instead of just being one responder, there's 3 responders. And if any one of the 3 responders accepts the offer, then that transaction happens. And the other two, they're called buyers in this game. The other two buyers get nothing. You can probably think to yourself what's going to happen in this game. If you compare the Monopoly game to the ultimatum game, what's the difference? The difference is whether or not these responders have any power to enforce the fair outcome. In the ultimatum game, absolutely you do. You have power. You have ultimate veto power. You can reject. Everybody gets nothing if you reject. But in the Monopoly game, it's just not true. You might say, I reject. You're being a jerk. I'm going to punish you. You get nothing. I reject your offer. But still, if one of the other two people accepts the offer, then that monopolist gets their money. You know what I mean? You may have your principles and say, oh, I'm not rejecting that offer. That's just not fair. I refuse to accept that bad offer. But the person who you're trying to punish is still going to end up getting their money because somebody else will accept it. So the question now, I don't really care about the monopolist in this game, right? I don't care about how greedy the monopolist will be. What I care about is comparing the behavior of the responder. I have some more slides about this. Okay, this is going to be the math. Before I get to the math, let's just think about the game. Somebody who would reject an offer of, let's say, 20% in the ultimatum game because they think it's too low. I think it was Kevin, right? Kevin was our example of somebody who really cared about equality and justice. But really, you know, most people reject offers of 20% or lower. That person, what would they do if they were a buyer in the Monopoly game and they were offered a share of 2? Would they reject it? What do you guys think? The only difference now is that you are one of 3 people who could accept this offer. In the ultimatum game, the offer comes to you and you alone. You either accept it or reject it. In the Monopoly game, you're like one of 3 people. If any one of them accepts it, the offer goes through. What do you think the prediction is? The person, let's take somebody who's like right on the fence of accepting or rejecting like 30%. Alpha equals 0.75. We just went through the math. If alpha equals 0.75, then your minimum share that you require is 0.3. 0.75 alpha, 0.3 share. Those two go together. 0.75 alpha, 0.3 share. So if you take a person that's like that, and now put them in the Monopoly game, and they get let's say they get a share that's less than 0.3. They get a share like 0.2. They get a share of 0.2. And the question is, will they accept that? Will they buy, which is to accept? And Peter says they're more likely to accept. I agree. I always agree. Would you mind telling us why? How do you know this? How do you?
The number of participants kind of dilutes that inequity aversion.
Okay, very good. And there's some strategy involved too, in the sense where you probably, I have to admit, there's a little hand waving here in the sense that I have to assume something about what I believe the other players will do. It sort of doesn't make sense to think about what's optimal for me in this case if I don't know what the other players are going to do. So if you've had game theory, this is a very standard thing that happens in game theory. You don't talk about whether something is optimal. You talk about where something is a best response, whether your actions are a best response to other people's actions. So if we borrow that concept from game theory and we apply it to the Monopoly game, but using the Fair-Schmidt inequity aversion payoffs, and remember, the whole point of those payoffs are to make a rational choice model of a decision maker to say they will choose the thing that maximizes their utility, including this concern about fairness and inequity. The question mathematically becomes, will that person who has an alpha of 0.75 now all of a sudden be willing to accept an offer of 2 that they previously were not willing to accept? The answer is yes, they would. Just like Peter, his intuition is essentially correct, that because there are these other players you're comparing yourself to, and also the fact that if you think any one of them is going to accept it, you definitely want to accept. That's easy. So let me talk about the math now, because we're running low on time. This is all about notation, how I should talk about the 4 players in this game. You know, read this if you want. I don't really care about teaching you like notation. Here's an important point. If you think at least one of the buyers is going to buy, then you always prefer accepting than rejecting. This is this bullet point here, the 4th bullet point. For any value of alpha or beta, someone with fair Schmidt utility would prefer to buy in this case, if you thought at least one of the other person was going to buy. Even if you're like extreme Kevin, where you really, really care about fairness and equity and justice, the model predicts that even somebody like that would accept a really bad offer if you thought somebody else would take it, if you don't. Here's another important conclusion. No matter how inequity averse the buyers are, the outcome where all 3 buyers accept any price below 10 is an equilibrium. No player could do better by changing their strategy. Here's another weird thing about game theory. Just because something is in equilibrium, it really doesn't mean it will happen. And I acknowledge that shortcoming of equilibrium. Oftentimes you analyze a game and you find an equilibrium, but if the players of the game aren't aware of this equilibrium, then they won't necessarily play it. However, the point I'm trying to make is that fair Schmidt utility can, even in a simple game, sorry, is that all I have to say? Let's go to this. If I compare the Monopoly game to the Ultimatum game using this fair Schmidt utility, I call it FS utility, where assume someone has alpha equals 0.75. I did this because we already went through that example. If they were a responder in Ultimatum game, they would reject 2.8. It's just not fair. But if they were a buyer in the Monopoly game, they would accept this outcome where they get 2, the other buyers get 0, and the monopolist gets 8. And this is a simple game which shows this point in the market setting. And of course, going from 2 players to 4 players isn't really like a market. It's still a pretty small game. You know, now instead of 2 players, there's 4 players. But even in that difference, the difference between 2 and 4, we can see a difference in behavior. People seem less concerned about fairness. And you just start to care about self-interest in that case. Okay, I think that's all I want to say about the Monopolist game. You guys have any questions about that? I think that game was studied in the mid-90s by Guth and all, the same people who studied the Ultimatum game. So they're like, hey, we have these results on the Ultimatum game. Let's probe further and see what happens when you change the power of the bargaining situation. And they thought of this game and they compared the results. And I thought, oh, that's a good game to demonstrate. Okay, let's talk about the behavioral economics of cooperation. I'm not going to have us watch this video. You can watch it if you want. You can click and watch that on your own time. It's a YouTube video that I did not make. But we've talked already about all these reasons why people cooperate. We haven't talked about inequity aversion. Maybe inequity aversion itself is a good reason to explain cooperation in the prisoner's dilemma game. How much time do I have? 1:33. I have about 15 minutes. I think that's fine. I'm just going to go through this stuff. Let's spend some time here. I want to argue now that this idea of a conditional cooperator, it's an important concept from behavioral economics, which is that some players prefer to cooperate with the other player if the other player is also going to cooperate. But they prefer to defect if they think the other player is going to defect. All right, so there's utility involved there. There are payoffs involved with that. And my point I'm going to argue now is that the Fair-Schmidt utility model with reasonable alphas and betas would actually predict that, would actually say, not only is it not strange that there are people who are conditional cooperators, but we would predict it. We would say, well, if this is your utility function, you should be a conditional cooperator because that is the way to maximize your utility. In other words, you play a game, you play the public good game if you want, you play the prisoner's dilemma game, you play golden balls, take any of these games. The best predictor of whether you will cooperate or defect is what you believe the other person will do. If you believe the other person will cooperate and you have this utility function that we described, then you will also cooperate. That's the prediction of the rational choice model. However, if you believe the other player will defect and you have the same model, the same utility function, but different belief, then you will defect. I think that's a pretty reasonable outcome of a model. So let's go through the math. Any questions? No. If the other player cooperates, well, first of all, let's choose which version of the prisoner's dilemma we're going to talk about. And this one that I have here in this payoff matrix, also called a normal form representation of a game. It tells you what your payoff is. It tells you the row players payoff first, then the column players payoff. So if I cooperate, you cooperate, we both get 3. If I cooperate and you defect, I get 0, you get 5. And the reverse is here. If I defect, you cooperate, I get 5, you get 0. If we both defect, we both get 1. This is actually the most common version of the prisoner's dilemma game. Okay. Let's now do the math. Let's figure out what Fair-Schmidt has to say about this game by looking at starting here at the second bullet point. If the other player cooperates, and I realize I'm not mentioning anything about beliefs in this. I just want to say that before you play the game, you can never be sure if the other player is going to cooperate. Even if they promise you, they say, cross my heart, hope to die, stick a needle in my eye, I'm going to cooperate. You still can't be sure they're going to cooperate. But with this bullet point here, I'm going with the presumption that your belief is very, very, very high that the other person will cooperate. What should you do? Okay. The payoffs are 3 for me, 3 for you if I cooperate, 5 for me, 0 for you if I defects. Sorry, that should say defect. If my Fair-Schmidt utility is with beta equals 0.75, I just picked 0.75 instead of 0.5. I think 0.75 is also a reasonable value for beta. I'm not saying, you change beta, you might change the prediction, but for right now, let's just look at what happens with beta equals 0.75. Then cooperate has a higher utility. Why? Here's more practice using the model. If my utility is 3, the utility that I get for having what this notation is 3 for me and 3 for you, it's equal to 3. Does everyone see where that comes from? Oops. Does everyone see where this comes from? The utility of 3 for me and 3 for you is simply equal to 3. Because my own payoff is 3, and I don't have to subtract anything because we have equal payoffs. I don't feel any envy. I don't feel any guilt. Therefore, my utility is 3 if I cooperate. Okay? I'll just say, ask a question. Please ask a question if you don't understand. What if I defect? What is going on here? Why does it say 5-1? It should say 5-0. I'm sorry, these are some, can I actually change these in real time? I want to change defects to defect. And I believe this should say 5-0, not 5-1. Maybe in an earlier version, I had a different payoff. Anyways, right? And actually, what is 5 minus 5 times 0.75? Oh, I don't know. something like 3.75.
Yeah.
So five minus that is it's still positive.
Yeah, it's 1.25.
1.25. Thank you. Okay. Now we're good. Let's go back to slideshow from current slide. I have 5 minutes left. That's okay. I'll be done with this in 5 minutes. Sorry for that typo. I fixed it. So this first line here is what happens if I cooperate. I'll give myself a utility, not a payoff, but a utility of 3. If I defect, I'll give myself a payoff of 5. My partner, my opponent, or the other player will have a payoff of 0, but my utility will be 5. Remember, that's my own payoff first. Subtracted from that payoff is any envy or any guilt. Well, I don't feel any envy. Good news is I don't feel any envy because I'm not getting paid less than the person. But I do feel some guilt because they get 0 while I get 5. What does the model say? I take beta, remember beta is 0.75, and I multiply that by, this should be 5 minus 0, which is equal to 5. That's how much I have to subtract because of guilt. And 5 minus, this becomes, you do right? Yeah, 3.75. 5 minus 3.75 becomes 1.25. So actually my utility is lower if I defect than if I cooperate. You guys see that? The rational choice model, in fact, that's the whole point of this model, is to be rational choice, is that this person should cooperate if they believe with high certainty that the other person is going to cooperate, because their payoff, their utility, I was wrong if I said payoff, their utility is higher if they cooperate, which is 3, than if they defect, which is 1.25. Okay? Now let's just finish it off and say, what if you think with very high likelihood the other player is going to defect? Then your payoff is also 1 and 1 if you defect, but 0 and 5 if I cooperate. In this case, it doesn't matter what your parameters are. It doesn't matter what alpha or beta is going to be. If you defect, you get a utility of 1. Why? Because my own payoff is 1, and I don't have to subtract any envy or any guilt. So it's just my utility is equal to 1. If instead I cooperate, well, of course, I get a payoff of 0. The other guy gets a payoff of 5. My payoff will be either 0 or negative. If I feel any sort of envy, then I have to subtract it from it. So it'll be 0 minus whatever envy I feel. I don't even care about that. The point is, I'm definitely getting a lower utility by cooperating than I do by defecting. So let's bring it back and say, what's the point of this? Look at the title of the slide. I've just explained conditional cooperation in the prisoner's dilemma using the Fair-Schmidt inequity aversion model. It says that I would predict that somebody with a beta of about approximately 0.75 would be a conditional cooperator in this game. I've already defined for you what a conditional cooperator was. You don't need this model to define conditional cooperation. In fact, we already see it. It's very common. Rather, it's the reverse. It's that this model can sort of rationalize the behavior that we already see. And that's the conditional cooperation. Is this model perfect? Absolutely not. I don't want you to come away from this class thinking, oh, there's only one model of pro-social behavior, and that's the Fair-Schmidt inequity aversion model, and all the rest of them are garbage. I don't really think that. I'm sorry if I gave you that impression. What I actually think is that it's the simplest one. That's why I'm teaching it to you, because it's one that's simple enough that you can understand it and you could answer questions about it on a quiz. If I ask you, here's a game. I could give you a different game with different numbers here. And I could give you the parameters. I could say if a player has alpha equals 1 and beta equals 0.5, then which of these choices, it won't be cooperate and defect. It could be labeled whatever I want it to be. I'm the instructor. I can choose the labels for my actions. But what you will be asked to do is, and maybe it'll be worth it to give you just like a homework where you can have some practice doing this, so you're not seeing it for the first time on a quiz, is um, calculate what the utility maximizing action would be for this player if they believe the other player is going to do this. Calculate the utility maximizing outcome for this player if they think the other player is going to do this. And then you can kind of get a best response mapping for that game. I might ask you to do that. Or I could ask you the other direction, which is what we did in the utility, the ultimatum game, which is if I say, if a person is indifferent between doing this action and this action, let's say a person is indifferent between cooperating and defecting when they think the person is cooperating, right? What would you do in that case? If I said, imagine a player who's indifferent between cooperating and defecting if they believe the other player is cooperating. What would you do? You would say, leave this utility is equal to 3, but you would change this utility. Instead of 5 minus 0.75 times 5, you would say 5 minus beta times 5, because this beta would become the parameter that you're searching for, that you're trying to find. And you would get the equation 3 equals 5 minus 5 beta. And you would solve for beta. That's perhaps the more complicated version. So I think what I would like to do is maybe give you guys some practice with this in the form of a homework. And maybe a kind of a low stakes homework. It's not going to be worth a lot of points or anything, but it'll give you just some practice. Ibrahim says, yes, please. I'm more than willing to do this because I just because I think the first time you do it on your own shouldn't be on a quiz or a test. So that's what I'll do. I'll probably give you some more time than just until the next class to do it. Unless you want it to be due next class. That would be the fastest way for you to get it back, get some feedback. Should I make the homework due on Wednesday? Kind of a small stakes homework question, but I'll make it due on Wednesday, unless you object. I don't want to interfere with the election and sort of voting plans or anything, but any feedback on that? What do you guys think? No, please. What does no, please mean? You don't want it to be
Sorry,
due
what was the suggestion?
whether it should be due on Wednesday or make it due like Monday or something.
Can we have it due Monday just so we have the whole day to vote?
I guess so. But I will say this, on Wednesday, I want to keep going. I'm not going to keep talking about this model the rest of the class. I have other stuff we need to go on to. But that doesn't, but you'll still have more time to do the homework if I make it due in a week.
Do you drop any of the homework assignment grades?
I wasn't planning, I know. I do drop a quiz.
Okay, yeah, that works. I'd rather have the quiz because quizzes are graded higher, I believe. I was just looking at the syllabus.
Yeah, quizzes are more important. Homework is a relatively small part of your grade. And in fact, the only homeworks I've had you do so far are reading responses. So I would make this one kind of equivalent to a reading response, I think. Most people say Monday, so I'll just make it due Monday. On Wednesday, we will have a class that goes on to the next topic, which is like more game theory, actually. So explain a little bit more about games and how people actually play games and how it's different than what game theory predicts. But we'll talk about that on Monday, on Wednesday. I'm fine with making the homework due Monday. Yeah. I mean, I could do it optional homework. I could say, fine, excuse me, here are some problems, but they're not worth any points. What I suspect is that people wouldn't do it. And therefore, you wouldn't get any practice. And therefore, when you did see it on a quiz or an exam, you'd be like, I don't understand this. He never did this in class, even though I did do it in class. But, you know, it didn't make sense to you. And so I think it'll help you to have maybe a graded homework assignment that you can turn in? I'm fine. Let's make it due Monday. Let's make it due Monday. Okay. Do you guys have any other questions?